So thanks a lot for the introduction, and I should really thank the organizers, because it was great to be here, not only for the location, that of course is great, but also because I learned a lot actually from the previous talks, so it's really good. And the second comment that I wanted to make is that I took quite seriously the comment that was made the very first day, namely that some repetitions can actually be beneficial in this context. So you will see that, so this is going to be a talk about many-body localization and integrals of motion, which of course is something that was already discussed, in particular by Dima Abanin, the first lecture on Monday. So you will see that there is a little bit of overlap with that, in particular in the first part, because what I basically want to tell you are essentially 5 things. So I'd like to start by recalling what one actually means when one discusses many-body localization from this point of view of integrability. So what are the properties of these integrals of motion? So in the literature, they are usually called LIOMs or LBITs. LIOMs, of course, stands for local integrals of motion. So what are the properties that you expect to be there for these operators? And also, why is it interesting to really think about the problem from, let's say, this perspective of integrability? And then in the main part of the talk, I just wanted to give some ideas of how do you actually try to construct this quantity explicitly. So how do you write down the shape, the form of these operators in terms of the original degrees of freedom that you have in your Hamiltonian. So I will just briefly mention some constructing schemes that have been proposed in the literature that are mostly numerical. Maybe they will be also discussed in the following talk. And then I will focus most on perturbative ideas to build these operators. And the reason is that, first of all, this is somehow a simple way to think about the problem. And secondly, it also allows to make connections with previous works that are very well, let's say, known in the literature. So the work of Anderson himself of 58, and also the work of Basco, Lehner, and Schuller. So you will see that the formalism is actually quite close to that one. And finally, in the last part, so I think Dima had no time to really present this, I would say, the only mathematical result that we have on many-body localization, which is this Imbri theorem for disordered spin chain. So I just want to give you the statement of that, and then, of course, we can discuss about the hypothesis and what would they imply, and also how is this connected to some recent debates again in the physics literature about stability and existence of MBL and all that. So if anybody wants to add comments on that, I would be very happy to turn this 5th part into some discussion moment. Okay, but let me somehow begin by recalling the idea. So I had a couple of slides at the beginning that actually have nothing to do with disordered systems. I wanted to briefly discuss another example that I think you're all very familiar with, which is the example of the quantum Ising chain without disorder. And the reason is that this gives you a feeling of how what we are trying to do with MBL is actually pretty natural. So the idea is that you want to do some change of basis, in this case in operator space, and find the right degrees of freedom in terms of which you can write down your Hamiltonian more easily, and you can somehow unveil properties of eigenstates and eigenfunctions of your many-body operator. So in the clean Ising case, you know what you have to do. So this is your 1D Ising Hamiltonian, and you know that, so you formulate it in terms of spins. You see that you have these usually Ising interaction terms, which couples nearest neighbors in your chain, let's say favoring alignment along some direction in the block sphere, so I call it X. And you have your transverse field in an orthogonal direction. And you ask what are properties of all the eigenstates and the eigenenergies of your system. And I would say that if you formulate the problem in this language of spins, it is not too easy to understand what the answer should be. So you can maybe guess things about the low energy sector of your problem. You kind of understand how the ground state should look like, depending on the strength of this field, or let's say normalized field. You also, I think, easily guess what are excitations on top of the ground state, which are intensive in energy. But if you really want to understand all the many-body spectrum, so even at very highly excited energies, I would say it's not so simple to do it in this formalism. And so what you do is to introduce new operators, which in this case are no longer spins, they are actually fermionic operators. You do it via the well-known Jordan-Wigner transformation. So you see this is a nonlinear transformation where you have creation and annihilation operators at a given site j of your chain. And these operators involve not only the spin at the site j, but also all of the spins which are sitting at sites which precede j along your chain. So it's quite a nonlinear and also in some sense non-local transformation that you want to do in here. But this is very helpful because then you see that your Hamiltonian can be rewritten as a quadratic Hamiltonian in terms of these spin operators. And then once you get such a form, you know how to proceed. So you see this is, if you choose well your boundary condition, this is translational invariant. So you know that you can go into Fourier space. So this is again a transformation in terms of operator. You write down creation and annihilation operators in momentum space by taking linear combinations of the original one. Your Hamiltonians now decouples because you are somehow in the right basis. So at this stage, it decouples in the following way. You still have a sum overall momenta, and you still couple, let's say, plus and minus k. But you now have sums of terms which do not talk to each other. You have 2 by 2 matrices, so you know how to diagonalize your 2 by 2 matrices, of course. So you will find the corresponding eigenenergies. You will find the corresponding, let's say, 2 components vector. And once you have your 2 component vector, you can introduce a new set of operators, which I call here d daga k dk, and the same for minus k. So these are just linear combinations of these guys, of course, with the coefficient given by the eigenvectors of this matrix. And if you do this, you end up with this form, which is now really simple. So this is really a sum of decoupled terms, where you see that you have each momentum that enters linearly in this sum. So you have the single particle energy corresponding to the given momentum. And then you have these operators, which are essentially number operators. So they tell you whether you have a fermion or not with that particular value of momentum. And in this formalism, the problem is essentially solved. So you know that these fermions do not talk to each other. So if you want to build the full many-body eigenstates, it is enough for you to understand what are these momenta, so the single particle states, and then you build the eigenstates with the appropriate fermionic symmetry. And if you want, what you can also say is that each of these many-body wave function will be just labeled by strings of numbers, one number for each possible value of momentum, which are either 0 or 1, and which tell you whether you do have such a fermion in your many-body system or not. And then you ask what is the energy of these states, and what you have to do is just to sum up all the energies of the single particle states that are there, and you get a spectrum. And you see that you are already essentially formulating your problem in terms of conserved quantities. So the conserved quantities that you have in here are just these number operators, which form a complete set in the sense that you can rewrite your Hamiltonian simply as a function of these operators here. So you do not have terms which are decoupled with a d daga of one momentum and a d of some other value of k. So this is very nice. Now you can ask a further question, which is, well, what do this new degree of freedom correspond to in terms of your original degrees of freedom, which were the spins, that are maybe those that you can actually manipulate if you're running an experiment with such an Hamiltonian. And you see that in this case, well, again, okay, of course you can retrace back all the transformation that you did, but there is some non-locality involved in this mapping, because you see to, let's say, create or destroy a particle at a given site, you actually have to keep track of all the spins, and these spins which appear in here can actually be arbitrarily far away from the particular site j that you're looking at. So the point is that when you discuss these problems that are many-body localized, you essentially want to play exactly the same game. So you want to identify operators which, in terms of which your Hamiltonian takes a sufficiently simple form that allows you to understand properties of the spectrum. And in some sense, you can do it let's say, with a smaller cost. And what I mean by this is that the type of transformations that you have to do to get these operators have some nice property of locality. So the object that you get at the end are obtained as some kind of local transformation of your original degrees of freedom. So this is the main idea of all this business. And now let me try to rephrase this in the context of these interacting disorder systems that we are actually interested in. So I will take the point of view of fermionic Hamiltonians here. Just for simplicity of notation, I put myself in a lattice of course, I will be interested in thermodynamic limit, so infinite volume limit for this lattice. And I have my usual interacting fermionic Hamiltonian with the local disorder. So you see the thing, yes. These are my, let's say, random variables. I have the kinetic term, and I have this interaction term. So let's say that you have density-density interaction terms, which involve fermions that are sitting at sites which are sufficiently close to each other. And we, let's say, are interested, of course, in the regime where this Hamiltonian is MBL. And so let me give, so there were many definitions of MBL in previous talks, but let me give some sort of informal, a bit sloppy formalization of this. So let's say, you find this extensively discussed, of course, in the seminal work of Basco-Alena and Schuller, but somehow the way you can also think about this problem is that when you are MBL, you take some many-body wave function, let's say that it's an eigenstate that I call psi alpha in here. You create some local excitation on top of this state, so you put an extra particle at a specific site I in your lattice, and what you find is a new state, which you can choose as initial condition of your dynamics, and the dynamics, which is unitary dynamics, is telling you basically that this extra energy or amount of mass that you're adding on top of your eigenstate, during time evolution, it will not, let's say, decay very fast to infinity due to scattering with the other degrees of freedom with which this particle can interact, but it will somehow remain in the vicinity of the site where you put it at time t equal to 0, which is a way to say that the time evolution of your wave function is not too far. It remains somehow localized in the vicinity of the initial condition, which is also a way to say that this state that you're creating by taking an eigenstate and adding a local particle is itself not too far from another eigenstate of your many-body Hamiltonian. So if you think of the problem in this way, it is natural then to expect, at least a posteriori, that there should be some sort of conservation law in your system such that the probability, let's say, to find this particle somehow nearby the initial condition remains large under time evolution. And this conservation law has to be local because, of course, you can probe them with local observables like local densities. Now, there are several limits of this Hamiltonian for which this can be made actually very precise. So let me skip this, which is perhaps too trivial, and let me discuss a limit that everybody here knows quite well, which is the non-interacting case. So assume that you switch off this interaction term, and then you go back to an Hamiltonian which is quadratic, like in the Ising case. And again, you know that even though you have many particles, they do not talk to each other. So your problem is solved in terms of the underlying single particle problem. So what you can do is you introduce your single particle Anderson Hamiltonian, you diagonalize it. So you will find eigenfunctions phi a and the corresponding energies. And then you build your eigenstates out of Slater determinants of these single particle states. Now, what it means at the level of operators is that, again, you can introduce new operators, which are creation and annihilation operators of particles in a state which is labeled by this index A, so in a single particle state of your Anderson problem. You have the associated number operators, and you see, again, these operators are linear combination of the original ones, and the coefficients that you have to put in here are just matrix element of your change of basis unitary operator. So you have a basis of your Hilbert space of a single particle, which is the basis of eigenstates of position operator. When you diagonalize, you identify another orthonormal basis, which is that of single particle eigenstates, and you know that the two are related by a rotation. Matrix elements of this rotation are just the components of this wave function at the different sites, so you plug them in here. You take this operator, you somehow plug the inverse, if you want, in here, and you realize that, again, your Hamiltonian takes this very simple form, so it's just a linear combination of your number operators. Exactly as in the Ising case. Now you have, again, a complete set of conserved quantities. The only thing that you have to ask is how local are the operators that you're building. And of course, this depends on whether your underlying single particle problem is localized or not. So you see, a priori, you're writing this object as a double sum which involves possibly all sites in your lattice. So it looks as if to build one excitation here, you have to involve all of your degrees of freedom in the lattice. But of course, you have these coefficients in here that are your wave function. So you know that when these objects are exponentially localized, these coefficients will be large only for those sites I and j, which are close to the localization center of the particular wave function that you're looking at, that is this phi a. And so in this operator expansion, the terms which corresponds to sites that are very far away from the localization center will be actually very small in norm. So this means that you can truncate also your operator expansion somehow to some compact domain in your lattice, and you get a very good approximation up to exponential errors of the conserved quantities that you are building. So this is somehow the notion of locality that is inherited from the localization of the single particle problem, and this is the notion of locality that you make use of also when you discuss integrability in these many-body localized systems. And here, there's just a comment about language. So people like to call these operators local. In many-body quantum physics, usually the term locality is a little bit weaker than this. So for example, in that setting, momentum operators are considered to be local. So it's very natural for us to call this local, but maybe quasi-local would be a more appropriate terminology in here. But anyway, whenever I will say local, I will mean local in this sense. So now what do you expect when you put back these interaction terms? So let me state this as an expectation for the moment, and then we will see to what extent this is actually shown to be true. So you expect that the same thing is true, so you can that you can again identify some set of underlying degrees of freedom which are associated to operators of this form, such that if you look at the number of operators here, these operators are independent. This is a word that I use to mean that they commute with each other. So you can diagonalize them simultaneously. They are conserved, of course. They are local in the sense that the norm is exponentially localized, like a single particle wave function. Again, the set is complete, so this means that all the eigenstates of your many-body Hamiltonian can be uniquely labeled by the set of quantum numbers associated to all these number operators. And there is a further thing that you may want to add to this, which is that you preserve somehow your original fermionic algebra. And this amounts to say that you basically want, as you did in the Anderson case, you want these operators to be related to the original one, so there should be an L here, sorry. So to be related to creation and annihilation operators in space by some unitary transformation. That, of course, has this property of preserving locality in the sense that you apply it to operators in real space and you get out something which is still, it's a small rearrangement of the degrees of freedom nearby the one that you started from before applying the unitary. And the fact that you have a unitary transformation in here is nice, as I was saying, because you somehow preserve the algebra. So in particular, you have that your new number operators still square to themselves, which means that you can still interpret them as occupation number of some particle-like excitations. So you can think of these degrees of freedom as representing quasi-particles, but now, of course, they are exactly conserved, so they are, in some sense, exact quasi-particles. Okay, so as you saw already in the previous, let's say, lectures, these were ideas that were, let's say, introduced and discussed mainly in this work of 2013. So this is Serbin, Papic, and Abanin. And there are two other works which are pretty close conceptually. So this work by Bauer and Nayak. So the language is a bit different in the sense that they don't talk about operators. They really focus on properties of unitary transformations that diagonalize your Hamiltonian, but somehow you see or you understand easily that this is very much connected to what we are talking about, and there is also this work by Hughes, Nankinshore, and Oganesian that is more or less simultaneous. And here I put just two reviews which are really specific on this topic of integrability in MBL, so they are both from 2017. You will notice in the literature that there are a lot of reviews in 2017, and this is due to the fact that there was a special issue of an Allender Physique just on MBL, so you find a lot of, let's say, references in there. which is perhaps useful. Okay, so again, why is it somehow interesting? So first of all, the idea is that exactly again as in the easing case, you can now rewrite the generator of your dynamics simply in terms of these quantities that you have identified, where you see that now, of course, there is a difference. So before you just had the linear term because your underlying Hamiltonian was quadratic. So quadratic Hamiltonian are closed with respect to these diagonalization procedures. If you add interactions, you have no longer a quadratic Hamiltonian, and this shows up in the fact that you have all these nonlinear contributions, which tell you that these degrees of freedom still interact with each others. But if you are MBL, there is a structure in here that is in the couplings that control the strength of this interaction that are expected to be themselves exponentially decaying. So you can associate some region of the lattice to each of these operators, which is the region where the norm is large. You can define distances, and therefore you can define decay of the strength of the interaction. And of course, this gives you access to the spectrum. So this is a little bit of the form of what you do when you have Fermi liquid, but now you have an insulator, so people like to call it a Fermi insulator. So the idea is, of course, to derive this form from your original Hamiltonian, but you will see that there is a lot of literature where actually this type of models is assumed from the start as an effective model of this MBL phase. And this is also interesting in the sense that once you formulate the problem in these terms, you can really deduce many properties of this MBL phase in a cleaner way. So let me give a few examples. So this, what I just said, corresponds to this characterizing in here. So you can use the structure of this interaction to deduce properties. So I just list here a few examples. You can derive what is the dynamical behavior after quenches of one-point functions, so expectation values of observables. So you will see that they will relax due to the interactions that you have between these degrees of freedom. They will relax actually slowly. You have power laws in here that you can work out in terms of properties of these interactions. You can really have a very good control of timescales of dephasing, and also of, let's say, how entanglement entropy behaves, again, following quantum quenches. You can even compute, so you saw a lot of results, also experimental results on these correlation functions like the imbalance. So what you can do using these integrals of motion is compute the value of the plateau of this imbalance as a function of parameters of your Hamiltonian, such as the strength of disorder. You can characterize stability of MBL, or try to characterize stability of MBL in this language. So this is connected to the last part of the talk. And you can also use this as a sort of theoretical framework to unify a bit all the different characterization of diagnostics of MBL that you find in the literature. So if you assume that conserved quantities with this particular shape and form exist, you can actually deduce from that several properties like vanishing of the dissipative conductivity using Kubo formula. This is what you find in Bascolet and Schuller. You can deduce localization in Fock space. So here I wrote Anderson localization. Actually, as it was pointed out, you have to be careful in terms of the scaling of this volume with system size. But OK, you can deduce the fact that the IPR is different if you are localized or delocalized. You can discuss area law of highly excited eigenstates. Violation of ETH, of course, follows from this. Absence of level repulsion if you are looking at level statistics. And also this logarithmic growth of entanglement that was discussed by Dima Banin the very first day. Now I put a third point in here, which is somehow with a question mark. So if you see this type of construction, you may immediately think that this is very interesting in terms of quantum information in some sense, because you now have identified in an interacting model a new set of degrees of freedom that are qubits. If you think in terms of spins, maybe this is easier to see, but it's the same in this particle language. which are exactly conserved by your dynamics and which are kind of local. So you may hope that by doing local manipulations on your system, you are able to actually flip these qubits or create excitations and so on and so forth. So you may hope to be able to use these quantities to do some quantum computing. But somehow the question mark in here comes from the fact that these quantities are interacting with each other, and so this creates dephasing in your system that is slower than in generic systems, but still it may pose problems when you really want to do quantum computing, because you also want to conserve relative phases, and of course relative phases are progressively killed by these dephasing processes. So now it becomes more a question of timescales. Exactly.
Experimentally, I would say not very.
It's not. I agree. So. Yes, I agree. So if you want to exactly move one of these guys, first of all, you need to know the expression of this in terms of what you can manipulate, which is not obvious. But then the closest, or let's say the thing that you can do so far, so I can show you something on this, is to really put yourself in a context in which disorder is so strong that these are really, really very localized, and you hope that if you flip one of your original spins, you are essentially kind of flipping one of these guys. So let me just flash, or maybe I'll do it at the end because there are many slides in between. And so there are some experiments that have been done to try to measure interactions between these guys, and the idea is to effectively act on your original spins and indirectly deduce from that the interactions between your quasi-particles. But I agree with you. I mean, this is part of the question mark, I would say. Okay, so having said this, let me just flash what are things that you can do to try to build these operators explicitly if you are given some Hamiltonian that you expect to be in this MBL phase. So you see there are many proposals in the literature. So some really rely on these ideas that you have a unitary that maps your position operators into these quasi-particles. So what they try to do numerically, is to write down diagonalization flows, so iterative procedures where you try to progressively eliminate the strongest off-diagonal couplings in your Hamiltonian, and you try to after this sequence of transformation to write an Hamiltonian that is only given in terms of number operators in your basis. And you find some references in here. There are also schemes which are more renormalization group-like, so which are similar to what people did to study ground states of disorder systems via this strong disorder renormalization group, adapted here to also to excited energies. So the idea here is similar to the one of diagonalization flow, except that you have some decimation step in between, so you freeze some degrees of freedom along the way. There are more, let's say, intuitive procedures that rely on the fact that what you want to build is local, or you expect it to be local, so what you can do is cut your system into local pieces and then do the equivalent of exact diagonalization of these pieces to find operators which are exactly conserved. And then you can do something more, let's say, writing down formulas, and this is very much relying on perturbative ideas. So let me try to very briefly give you the idea of this and make connections with the previous literature. So let me start from the naive, let's say, perturbation theory that you can think about. So first of all, what is the perturbative parameter? So we saw that if you have a non-interacting Hamiltonian, you know how to find this complete set of conserved quantities, which are just occupation numbers of single particle states. So the first step here is to rewrite your Hamiltonian in the basis of these Anderson states. So this is disorder plus kinetic energy, and then you have the interaction terms, which in this language are these generic 4 fermion terms where you create and annihilate states at different, or labeled by these different A, B, C, and D. And I put a lambda in front, so this means that I assume the interaction to be small, and I try to do perturbation theory in the interaction. So it's a bit like Landau ideas for constructing quasi-particle by dressing the non-interacting particles of your system. So naively, what you would do is, well, you would write down an expansion like this. You start from your Anderson number operator, and then you write down terms in powers of this small parameter, and you try to fix these terms, imposing that this operator is conserved. So this will give you, at any order, an equation like this. You want to solve for the kth order, you have the kth minus 1, so you need to invert this commutator with a non-interacting part of your Hamiltonian. So you check that you can do this, so that this object here is not in the kernel of this commutator. This you can show that is true under general condition. And then you can write down the solution for such an inversion that formally looks like this. So the reason why I wanted to write it down is that you see that it looks a little bit like a time averaging that you are doing in operator space, and this brings you back to some other proposals that were done before in the literature of constructing these conserved quantities simply by time averaging local observables in your system. So it's a bit similar. It's not identical, but somehow the idea is not too far. And there are extra terms in here which come from the fact that this equation does not fix uniquely your kth order terms. So you see you can add arbitrary operators here which commute with H0, and you are still fine in solving this equation. And what you can also show is that you can fix uniquely these extra operators, imposing that what you're doing is essentially a unitary rotation, or at least that preserves this property of having number operators order by order in your perturbation theory. So just to give you an idea, if you do it at first order, you will get out terms like this, where you see you have your 4 fermion terms here. These indices are again single particle states, and you have factors in front that have this usual form of being ratio between matrix elements of the interaction and energy differences of single particle states. And then you ask, does it make sense what you are doing? So you are doing perturbation theory, but is there a regime where this converges to some operator which has some nice property of locality? And now, as you may know, if you do naive perturbation theory like this, the answer is always no, so it never makes sense. And the reason is that you have this problem of local resonances, which make it so that your perturbation theory always diverges for reasons which are not connected to localization or delocalization, but they are just connected to the fact that you will, with probability 1, you will find some of these terms, or let me call them locator in the language of Anderson, at least one of these terms which is large, because the corresponding single particle energies are resonant. And of course, terms of this form will appear in your perturbative expansion at any higher order at arbitrarily high powers. So you have full subsequences which are diverging in norm. So you should do things carefully. So you should, for example, be a bit careful about doing some resummation of these apparently divergent subsequences and keeping your regulators finite while you do this, which is somehow what you find already discussed in this in the work of Anderson. So Anderson was doing perturbation theory for the resolvent, and he still has the same problem in the sense that you can write the propagator between two sites in a perturbative expansion, in that case in the hopping. You have these divergent terms, but you see that somehow you can resum these divergent terms, and this will give you some renormalized perturbative expansion where you have some, let's say, self-energy corrections to take into account. So in his language, you can reduce the problem to the, so originally your resolvent will be a sum over all path in your lattice, which connects two sides. And what you can do is to rewrite it as a sum over only paths which are self-avoiding, so that you get rid of this problem of hitting several times sites which are resonant. So this is what he calls the forward scattering approximation. So we want to do basically the same thing at the level of operators, but for us it's convenient to start by rewriting our expansion in this way, where you see I have my original operator, and then I sum over all possible strings of arbitrary length of creation and annihilation operators, which I will generate order by order in perturbation theory, and I put an amplitude in front, which resums all of the amplitudes that I get at arbitrary order in my lambda, in my perturbative expansion. And if you cast the problem in this way, then you see that if you impose that this operator is conserved, you get some linear equations for these amplitudes or coefficient, and these linear equations look really like a Schrödinger equation. So you can kind of interpret all of these amplitudes as amplitudes of some effective single particle wave function. So for each operator, you have one wave function. And this is the amplitude of a wave function on an effective site identified by these strings of, by these index sets, let me call them like this, in an underlying lattice that we call an operator lattice, because basically for each site of the lattice, you have one operator in your expansion. And now you can argue that if your single particle problem is Anderson localized in this lattice, then you are in business because these amplitudes will be somehow exponentially decaying. And so you are writing down an expansion which is convergent in norm to something that is localized, and therefore which has the properties that you are looking for. So you have to show this, and this means that you have to study what are the properties of this underlying effective single particle problem. So you have to understand the structure of your lattice induced by your commutation equations. And what you find is that this lattice looks very similar to some sort of beta lattice. So this brings you back to these ideas of MBL like being very much similar to Anderson localization on beta lattices. So this means here that you can group all of your sites into generation according to the lengths of your operators. You can define connectivity. You find that you have a connectivity only between one generation and the next, and this is direct, or between sites in the same generation. And what you also find is that the effective connectivity from one generation to the next is typically much larger than the one that you have between sites in the same generation. So this you can work out. The effective connectivity between generations is a function of parameters of your underlying single particle problem. So it's here the ratio of the bandwidth of your single particle problem divided by the typical level spacing in volumes of size of your localization length. And so this suggests a very natural approximation, that is to neglect jumps between the same generation and just keep the one from one generation to the next. So this is the approximation that we also somehow do to solve our problems. And I just want to point out that this is exactly similar to this forward scattering approximation of Anderson, and also to this imaginary self-consistent Born approximation of the BAA paper. So if you rephrase this in terms of diagrammatic, it means that you are considering only tree-like diagrams in your expansion. But for us, it means that we can now solve explicitly for the expression of this amplitude. And you see, you can write them as sum over path in this lattice from the root to the side that you're looking at of product of locators, which have the form that I kind of showed to you before at first order. And this is nice because given this form, you can also make connection to glassy physics, but okay, that's another issue. What is nice in here is that once you have this expression, you can derive bounds for this amplitude. So you can really show that there is a finite regime of parameters which corresponds to the interaction being small enough, such that you can actually impose exponential bounds on the decay of these amplitudes, asymptotic in the distance of this lattice, with probability which goes to 1 asymptotically. So you can argue that your operator expansion converges within this approximation, and you have an estimate of the radius of convergence, so of the strength or the weakness of the interaction that you need. And those of you that know beta lattice localization, they will recognize this formula. So this is very similar to what you get actually on single particle problems on the beta lattice. Okay, so the last comment is, as you see, this is let's say a procedure that is constructive. It allows you to connect to previous work, but of course it is approximate. So you may wonder whether you can go beyond this. So what you are doing in this approximation is essentially to neglect some corrections that would be generated by this resummation due to resonances, corrections in these energy denominators. So you may wonder whether it is dangerous to do this, or in general, if you can go beyond this and say something rigorous about existence of integrals of motion in MBL problems. And so let me just mention this work by John Imbrie, so you may know already about it. But the idea there was to look at, so what he does is to look at spin chains with disorder. So you see you have many terms in the Z basis, and then you have this sigma x that is the equivalent, of course.
Mm-hmm. And we know it's not exactly the
I don't know.
This hyperfixity model has no dynamics. That's something which is a very specific thing.
I don't know. I think in numerics you do see differences clearly. At the level of proof, there is no generalization of these two XXZ. So there might be something that really comes from this structure in there, but I wouldn't know how to pinpoint.
Proof is for a model which has itself its own little peculiarities.
And what is actually the proof? So again, this is the equivalent of our interaction, is the small term. And what he shows, so there is an assumption here that maybe is of interest for mathematicians, but I like to rephrase it in terms of, okay, what he is asking is that if you take boxes or finite volumes of size n of this Hamiltonian, the smallest gap that you find between eigenfunctions of these finite volumes is no smaller than some exponential in the dimension of the box, which is kind of reasonable, but of course, okay, one can discuss about this. And under this assumption, the proof is that, so it's stated here, but let me also rephrase it. The idea is to show that the many body wave function that you get are very similar to product states in this SZ basis, which is to say that if you look at expectation values of SZ, you find that this is very close to 1. So let me, okay, I'm almost closing, but what I find, what is really interesting in the proof is actually, in the theorem is actually the proof, because the way he does it is by means of some multiscale diagonalization procedure of the Hamiltonian, where at each scale what you do is you use perturbation theory where you can, and where you have these resonances you do some non-perturbative rotation in there, so it's like doing degenerate perturbation theory. So he actually characterizes this unitary, and if you know that this unitary preserves locality, then you get for free that you should have conserved quantities with the right local properties. But it's a math statement, so what it means is that it doesn't tell you how small this gamma should be. So there is no estimate of what is the smallness of this, let's say, localization breaking term. And this is just the final comment I wanted to make, and it is the fact that it would be very useful actually to have also an estimate of that, because a lot of the discussions that you find in recent physics literature about stability, and there are even people that claim that even in 1D MBL is unstable in the sense that the critical disorder strength that you need should scale with system size, so it's not a phase what you're talking about. So these are claims which are based on numerics, which are of course in contrast with what is proven for the particular Imbri Hamiltonian. So the final comment here is that if you want to somehow coincide or let's say be happy with all of these results, it would be really nice to somehow generalize these type of proofs, not only in terms of the model that you're looking at, but also giving some, let's say, explicit estimate of radius of convergent, because this will give a feeling of why we should worry or not about numerics not showing, let's say, MBL the way you want at values of disorder that are, let's say, reasonably small and not extremely large. So here I think it's nice this setting here, because there are both physicists and mathematicians, and I think this is precisely one of these problems that needs both type of inputs. So if anybody wants to work on this, I think it's a good problem. Okay, so I think that's it. Mm-hmm.
To show that where his approximation was exact.
Yes, even in the Bethe lattice, the prefactor you get it wrong with even in the large connectivity limit of the Bethe lattice. So you do that approximation, you get exactly this k log k. So he would have opping here instead of interaction. You get this k log k, but this prefactor you have to work. You have to keep self energies to get this prefactor right. But yeah. No, that's slightly different. So what you're referring to are, and scars is an example. So you take all your many-body eigenstates, some of those will be thermal, and maybe there are special ones which have properties of low entanglement that look like MBL. So this is one possibility. What I'm referring to in here, oh, sorry. No. Oh, I forgot, okay. Is the fact that, so you can then ask, how does this break down, this stability of the localized phase? And there are some scenarios, so this came up already, this avalanche scenario that gives you somehow some critical threshold. So what you do is, you take an MBL system, you plug in some subsystem which is thermal and, let's say, delocalized, and you ask whether the degrees of freedom that are localized close to it actually hybridize a lot with this, and how much this bubble expands. And you find critical thresholds for the coupling between your seed and localized degrees of freedom far away, such that if you exceed it, the localization is unstable and you should eventually delocalize. And then you try to extract these values numerically, and what you find is that your threshold is met somehow for values of disorder which are much larger than the values that you find with other diagnostics like spectral statistics or all the things that I think will be discussed later on. So there is somehow a window in disorder where this criterion will tell you that at large times and large system size you should be delocalized, but what you can probe tells you that you are localized, and so people now propose to distinguish between the true transition and the true, let's say, localized phase, and this regime where perhaps at very large time scales and length scales you will eventually, let's say, thermalize, and if you want, the state that you're looking at is metastable in some sense.
Okay. Dennis? So here in your talk, beyond your just like thermonic number of operators, something that has 0 and 1 eigenvalue. And it has, I mean, it's 2 by 2 matrix.
Yes.
What is the general technical, what can it be? Because yeah, writing your Hamiltonian in terms of commuting operators, I mean, these operators themselves can be complicated. And here you are taking that these are just, sigma z.
Yes. So it's not. Yes, it's not even true in the sense that when I do this game of mapping of writing terms in this way, I'm not exactly keeping all terms in here that conserve my number operator structure. I'm throwing away these terms, so the things that I get do not even square to 1. So the operators that I'm actually constructing are not number operators. But if you do that through a unitary a la Imbri, then you know that the algebra is conserved. So you have both, let's say, of course the operators that you will are not unique, so the set of operators are not unique. So the question is, depending on the procedure, you can build stuff which is local but has a spectrum that is more complicated, and this is what we do perturbatively. Or you can try to work on this unitary directly, and this will guarantee that you have things that are number operators. So I wouldn't want to say that, let's say it's clear that you should get